Yeah, hello everybody. I'm starting today a session in a series of sessions on my model for reality, which is called the DIM model, Dynamic Interval Moment Model. And the first lecture will be about time. Time will be something different from what you expect, I guess. So let's begin with time. If you ask a physicist what time is, he will say time is what the clock measures. We will talk about that later. But I want to go back, and in this series of lectures, my point of view is not so mathematical. I am a mathematician, as probably you know. But the inspiration for the model comes from life more. So there is a better relation with biology, I would say. And I will not force a mathematical model on reality. I will try to observe things, as everybody does, and from these observations make the model. And then the mathematics, which probably comes in, is sort of dictated by a logical interpretation of the model. So that's different from the usual point of view in physics, where you embed everything in a geometry. So now about time, as I said, biologically, I want to go back to the beginning, to the very beginning when single cells were drifting around black smokers in the single cells, or blobs of chemical substances coming from a volcano outlet at the bottom of the ocean. And so these, like oil drops you could say, they developed a membrane which was a little bit tougher than normal, and it became a kind of skin. That's very important, because it separated the inside from the outside. And there were outside interactions. The temperature was going up and down, and maybe day and night differences, or volcano differences. So there was a periodic, usually, interaction from the outside, and the chemical substances inside reacted to these outside interactions. And so we got a kind of regular interaction. And maybe it took millions of years till at some moment these regular interactions were observed, or first experienced, I should say, like a thermometer measuring temperature. He measures it, but he doesn't know what he's doing. So when at some moment there was some kind of realization that some interaction is compared to a foregoing interaction. So you cannot do that if you don't have a primitive memory. So the first thing after the skin and the kind of feeling, so the first sense that developed is touch. And to use this touch, you need some primitive memory. So if you feel a kind of bump on your skin, or the temperature goes up, and it goes up regularly every day or so, through millions of years you recognize, you compare the two events, and you say, hey, cells don't say hey, but I do that. It's the same, or it's comparing, it's more or less the same. And so you need, as I said, skin, or membrane, and primitive memory. So these things, the use of skin and the memory, develop together in an evolution over, I don't know, I have no idea, millions of years, I think. These things go very slow in the beginning. At the moment they go much faster. But in the beginning, we had all the time of the world. So the primitive memory allows you to recognize some interactions. Recognize them. Why is that? Well, for example, some temperature is going up and down, maybe some electricity is, some lighting is, I don't know, several effects are there. And then the chemical substance in the cell begins to move by these reactions to the interactions. And the moving is also regular. And so there's some kind of friction and so on, and there develops some organelles in the cell. So the cell becomes more complex. So the cell sort of grows complexer. Okay, so by recognizing and comparing, you have to know that one thing is before the other. There is order. We discover order. The first was the first, the second is the second. Okay, you compare them. To compare them, you have to know the first first and the second second. So you realize there is an order. So at that point, when we discover order, you can already say, I get my first idea about time. Time is something sort of regular interactions, periodic, regular, and there is an order. It's ordered. So, with this primitive system in a cell, I can already formulate my definition of time, which is not the usual definition, I guess, but it's a very generic one. I want my theory, which will be developed, to be very generic in the sense that it uses the minimal assumptions, so that all other theories like relativity theory, quantum theory, are specializations of my theory. That means you add extra assumptions and then you continue. So I want to be very minimalistic. At all moments I will try to do the least thing which I have to accept in the description. So I do not assume any manifold or geometry, certainly not for the moment, but I just build it up from sort of biological beginnings. So, okay, we have this primitive memory is necessary, we discover order, so perhaps the definition of time could be, so I will write it here, time, a totally ordered set. So that is the definition I will use, a totally ordered set, which is very little structure to work with. What is a totally ordered? I will describe, I will introduce some notions which are sort of mathematical, but also very common. I will first define a partial order and then a total order. So a partial order so this is sometimes called a poset, partial ordered set, is given by some relation, say this symbol larger or equal to. And what properties does this have? So you have a set X and you have X and Y. This means elements of X. So a set is a collection of things. X and Y are such things. And you say that X is smaller than Y. That's the relation we define. And what are the properties? Well, there are three properties. The first is called reflexive. That means that X is smaller or equal than X. That's trivial, X is equal to X. It's antisymmetric. That means that if X is smaller than Y and Y is smaller than X, then X is equal to Y. There's no symmetry. And the third is perhaps the most special one. It's transitive. Transitive means that if I have X is smaller or equal than Y, Y is smaller or equal than Z, then X is smaller or equal than Z. So if you have the two relations in a sequence, then the first and the third are also related. Okay, so reflexive, antisymmetric, transitive, RAT. That's a partial order. A total order these are mathematical notions, but I will not use deep mathematics, only very essential things and almost very trivial, let's say. total order is the following. For every x and y and x, so if you take two things in your set, then either one is x is smaller than y or y is smaller than x. They're ordered. And either this or that. Well, and if they're both, then they're equal. Okay, so this is the order is total. Now, in physics, you use the real numbers for time, which is a big leap from a totally ordered set. The real numbers, I'm not going to define them. I will write R. And the rational numbers, Q. So these are the fractions. These are real numbers. Now, I'm a mathematician, but I'm not going to use numbers in my description. Why not? Well, there is no proof, and there is not even evidence that you can measure with numbers. What physicists do, they say, okay, let's fix a unit, and then we measure by a certain number times the unit. And the number is usually the real numbers, not the complex or the quaternions or something else. No, the real numbers that they use. Why? Well, because there's some topological reason for that. But the Greeks were using only the rationals, by the way, so, and they were discovered to discover the square root of 2, for example. But, so, why do you think that you can measure temperature with some real number times some degree, Celsius or whatever? With the same numbers you measure distance, temperature, but temperature, you cannot use all the numbers. It stops somewhere in the negative part, minus 273. There's a minimum. Perhaps there's a maximum, but that's very high maximum, perhaps. I don't know whether they know whether there is a maximum. What it is, there is certainly a maximum. It cannot be infinite, but okay. So I'm not going to do that. So my theory will be very generic, but you cannot calculate by equations in it. And that is, in my opinion, good, because nature is not made for that. I will explain this much deeper in the rest of the lectures. That this is in our cognitive system, but not in the natural world, not in the reality. So, my time is just a set which has a partial order which is total. And you can use the real numbers if you want. I will not do that. But you could also use a Euclid line. Euclidean line. Where you use the order given by the compass. You take a point, and another point, and here is the compass width. That is not a number, unless you decide to measure the compass width. So Euclid, in his famous plane geometry, did not want to introduce numbers because he thought that nature should not depend on numbers, and that was a very good thing. For us, we are nowadays completely indoctrinated by Descartes and the Cartesian geometry, where you use numbers and coordinates, and you think of everything as a set of points with coordinates. So I will not do that. So that means that my model will be, in some sense, very primitive, but surprisingly, I would say, the elements which are very primitive, whether you follow this all the time, you get some rather complicated theory, and that's what I want to explain. Okay, so we have some idea about time, and of course, I said the memory plays a big role, and using one sense is enough. One sense, touch, was enough to discover time. Now we have several senses, and they do not help much more in time, because the other senses are not direct. When you see something, this is the reflected light. When you When you smell something, this is some evaporated gas or whatever. So all the other senses are indirect. Touch is the only direct. Of course, physics depends a lot on light. And light we can see. And so there is the famous saying, I will believe it if I see it. But that is of course wrong. But it was for a long time a good argument. So the role of light in the physics will come from this fact, plus from the definition of the manifold in the relativity theory where time is used, depending on the velocity of c in the quadratic form. I will explain that later sometime. So there will be certain mixings of the mathematical indoctrination we have had with our ideas about nature. And this is completely ad hoc. It's fine, we have approximations and we have good results and we have applications, but it's not correct, of course. And the mistakes can be serious at the fundamental level. That's my point of view. So we have time. I said observation plays a role in time. And what comes from this combination of observation and time is the change. When the cell first identified, perhaps wrongly, or approximately, it was identifying that one interaction with another interaction, said it's the same. And that from one interaction to another, and a little bit different, you discover change. So change is an effect of time, of course, but change is not equal to time. Now you say change, yes, but change from what to what? Therefore, we have to invent some version of the universe. And I will have time now, and I have to define what kind of objects are there. So, which objects? Change of what, you can say. So I have to define objects, and okay, we have several possibilities with objects. We can observe them, maybe. They can exist. And there's something else, which I will explain in a moment. Okay, so normally we think that we observe something which exists. And that means that I have to give a definition of existence first, and then observing. But the time for this session is already finished, so I will stop here. And in the next lecture, I will describe the space, the objects, and the beginning of the universe.
Ja, ik denk, we moeten beperken, het is 20 minuten, dat is goed.
Ja, het zal er. Ik heb niet alles gedaan wat ik hier op die bladzijde geschreven heb, maar
ja, maar
ik heb toch